Science fiction is filled with stories where humanity must abandon Earth due to pollution, overpopulation, or nuclear war. But is launching the entire human race into space physically possible? In this fascinating exploration from Randall Munroe's best-selling book What If?, we dive into the staggering energy requirements, physical barriers, and audacious engineering solutions required to move 7 billion people off-planet. To determine if a planetary evacuation is plausible, we start with an absolute baseline energy requirement. For gigajoules per person, moving a 65-kilogram person out of Earth's gravity well requires at least this much energy, roughly equivalent to a megawatt-hour, 90 kilograms of gasoline, or a cargo van full of AA batteries. Multiplying this by 7 billion people yields 2.8 XYP joules a petawatt-hours, which represents about 5% of the world's annual energy consumption. While immense, this baseline is not physically implausible on paper. In practice, utilizing traditional chemical rockets demands vastly more energy due to a fundamental limitation. Rockets must lift their own fuel as you add fuel to launch a heavier spacecraft. The increased mass requires even more propellant in an escalating chain reaction, launching all of humanity, totaling roughly 400 million tons. Using traditional rocket fuels would require tens of trillions of tons of fuel, depleting the remainder of Earth's global oil reserves and making chemical rocket evacuation practically unfeasible. The mathematical foundation of space travel is governed by the Tsiolkovsky rocket equation, which relates the change in velocity delta V to the exhaust velocity of the propellant. Overcoming Earth's gravitational pull requires an upward velocity of approximately 13 kilometers per second, given that chemical exhaust velocities are limited to about 4.5 kilometers per second. The resulting mass ratio requires at least 20 to 50 kilograms of fuel for every single kilogram of spacecraft launched into orbit. As alternatives to chemical rockets, scientists and science fiction authors have proposed radical concepts such as the space elevator. This audacious idea involves anchoring a tether to a geostationary satellite held taut by centrifugal force, allowing electric climbers to ascend into space using ordinary electricity. However, the primary engineering roadblock is that the tether material must possess tensile strength several times greater than anything humanity can currently manufacture, leading engineers to jokingly rely on carbon nanotubes. Another astonishingly plausible method for lifting massive payloads is nuclear pulse propulsion. The concept involves dropping nuclear bombs behind a heavily shielded spacecraft and riding the explosive shockwave into orbit. Theoretical physics suggests that with a well-designed pusher plate, the craft would not disintegrate and could potentially lift entire city blocks into space, though the safety and geopolitical risks are staggering. The engineering principles behind nuclear pulse propulsion were considered so viable that in the 1960s, under the guidance of physicist Freeman Dyson, the U.S. government actively attempted to develop this technology under the codename Project Orion. Although the program was ultimately cancelled before any prototypes flew amid terrifying concerns over deploying massive nuclear arsenals into the atmosphere, it remains one of the most remarkable propulsion studies in history. Ultimately, while launching a single individual or a small crew into space is entirely achievable, attempting to evacuate the entire human population would tax global resources to their absolute breaking point and risk destroying the very planet we inhabit. As Randall Munroe concludes, leaving Earth en masse is truly a small step for a man, but an insurmountable leap for mankind.